Hello and welcome back to the Science of Concrete Materials class. This is lecture number 8 of the class. We will continue our discussion on the cement module of the class. So far we have covered these topics here, grayed out. Today we're going to start on the hydration, as I said. In this part of the module, we will start on the hydration of cement and its microstructure, the microstructure of the cement paste, that is. So we will basically study the hydration and eventually the paste structure, and we will touch on the structure of the concrete. Okay, so as our ultimate goal is to understand and predict the behavior of the concrete as a material, of course, due to its importance, as we have seen in the introduction. This requires understanding of the microstructure of the concrete. Concrete is a composite, heterogeneous material. So it is very difficult to build realistic models of its microstructure from which the behavior of the material can be reliably predicted. However, knowledge of the microstructure and properties of the individual components of the concrete and their relationship to each other is useful for having control on the properties. We will, of course, study the three components of the concrete microstructure, namely, the hydrated cement paste, the aggregate, which will be covered in a different module, and we will take a look at the interfacial transition zone between the cement paste and the aggregate. This really what constitutes the concrete matrix overall. Finally, also microstructure property relationships are discussed with respect to their influence on strength, dimensional stability, and durability of the concrete. So in the next few lectures, we will study the hydration of cement and the resultant products. We will study in detail their microstructure and how the hydration products form and their influence on the properties of the cement paste and eventually the concrete. We will look, as I said, we will have an introduction on the ITZ, the interfacial transition zone between the aggregates and the cement paste, because it has its own special properties and it impacts the concrete properties a lot. Okay, so the setting and hardening of the concrete are the result of chemical and physical processes that take place between cement and water. We need an adequate understanding of the chemistry of hydration for full appreciation of the properties of cement and concrete, and this what will be discussed in this part of the class. So far, and during the study of the cement and its composition, we have been introduced to some of the chemical reactions that take place during the hydration process and the resultant products. Now we will study in detail these, the hydration process and how the microstructure form. So let us define what a structure is and the different levels we are dealing with within the science of concrete. Okay, so the definition, what we mean by structure. Structure is defined as the type, amount, size, shape, and distribution of phases present in a solid. The gross elements, of microstructure of a material can readily be seen from a cross-section of the material, whereas the finer elements are usually resolved with the help of a microscope. So the term macrostructure is generally used for the gross microstructure visible to the human eye. The limit of resolution of the unaided human eye is approximately 1/5 of a millimeter, about 200 microns. The term microstructure is used for the microscopically magnified portion of the macrostructure. The magnification capability of some of the modern, electron microscopes is on the order of 10 to the power 5. And that's very powerful. So the application of transmission and scanning electron microscopy techniques really has made it possible to resolve the microstructure of materials to a fraction of 1 micrometer. Imagine, that is very powerful. As you can see here, this is the cross section of a concrete, just as what you see with an unaided eye, and this here is the what is resolved with the help of a scanning electron microscope. You could see like the ettringite needles, you could see them calcium hydroxide crystals. So it gives us really great insight to the study of the cement microstructure. Okay, the hydrated cement paste comprises the following components you will see here. Don't worry, we will go through them in detail in coming up lectures. But as you can see, what we will have, we'll have the solids, which is the calcium silicate hydrate. I defined that before. Calcium hydroxide, ettringite, monosulfate hydrate, other monosulfate, compounds other than the ettringite, and we will have residual unhydrated cement. We will have also voids within the microstructure. We will have entrapped air. This is, from the mixing process, larger than 1 millimeter. We have entrained air. This is what we intentionally entrain into the concrete, mainly for the freeze thaw resistance, and of course it has other advantages. It helps workability. We have the capillary pores, we have the interlayer space, and we have the micropores. Of course, we have water also present. We have the capillary water, the adsorbed water, interlayer water, and the chemically combined water. Okay, so the chemical reactions describing the hydration of the cement compounds have been really worked out through the study of the hydration of pure cement compounds. It is assumed that the hydration of each compound takes place independently of others that are present in Portland cement. This assumption is not completely valid though, since interactions between the hydrating compounds can have important consequences. But in most cases, it provides a reasonable approximation to understanding how cement hydrates. So let us begin with the hydration of the pure compounds. Okay. First, the calcium silicates phases. The hydration of the two calcium silicates, the first equation and the second equation, the C3S. Okay, sorry, this one's supposed to be C2S. Okay, the second one, C2S. That's a correction here. The first equation describes the hydration of the C3S, and the second one for the C2S. As you can see, these reactions are, stoichiometrically very similar. Different only in the amount of calcium hydroxide formed. Okay, as you can see here, the C3S combined with 11 molecules of water and will give us this compound. This is calcium silicate hydrate gel. I'll talk about it in the next slide. The same thing here. as I said, the principal hydration products is a calcium silicate hydrate, as I have shown in the previous slide. The formula, the C3S2H8, is only an approximate. It's an approximate formula, because the composition of this hydrate is actually variable over a wide range. This product, the C3S2H8, is poorly crystalline material that forms extremely small particles in the size range of colloidal matter, less than 1 micron. The calcium -S-H really reflects these properties. We use the hyphen to indicate it's an approximate composition and not exact. The properties, as I said, of this hydration product, will be discussed in more detail later, so we will elaborate more on it. In contrast, the calcium hydroxide is a crystalline material with a fixed composition. Both of the previously described reactions are exothermic, which means that heat is released as the reaction progresses. This heat will raise the temperature of the concrete, unless quickly released to the surroundings. So remember that, especially when we are dealing with large concrete sections. In the laboratory, hydration can be followed in a special calorimeter. I talked about this when we talked about the tests on cement. By monitoring the rate of heat conduction needed to keep the temperature constant. So the reaction sequence is most really conveniently described by reference to the calorimetric curve I will show on the next slide. That describes the rate of heat evolution with time. This curve right here. So the heat flow is proportional to the rate of reaction and is easily measured in the case of C3S, which is the compound of major interest. Okay, so let's look quickly at these stages and what happened in each stage. 1, 2, 3, 4, and 5, and with time, and this is the rate of heat evolution, calorie per gram. So when first mixed with water, there's a period of rapid evolution of heat, which is stage 1. Which this stage, ceases within about 15 minutes. There follows a period of relative inactivity, the induction or dormant period, stage 2, which is the reason why Portland cement concrete remains in the plastic state for several hours, which allows transportation, placing, and finishing. Okay. Initial set occurs in 2 to 4 hours. At the time, C3S, has begun to react again with renewed vigor at the end of the induction period right here. As you can see, there's an acceleration period. The silicate continues to hydrate rapidly, reaching a maximum rate at the end of the acceleration period. Okay, then we have stage 3, which corresponds to the maximum rate of heat evolution. By this time, about 4 to 8 hours, final set has been passed and early hardening has begun. After that, the rate of reaction again slows down, as you can see in stage 4, until it reaches a steady state stage, which is the stage 5 right here. This within, about 18 to 36 hours. Here in this table, you see these are the processes, that occur in each stage, as shown in this table. It shows, each stage, the 5 stages I just described, the kinetics of the reaction, whether it's chemically controlled, what happens, what controls the reaction, the chemical processes, hydrolyses, formation of hydration products, etc., and their relevance to the concrete properties. I will describe them in detail now. So on stage 1, on first contact with water, calcium ions and hydroxide ions are rapidly released from the surface of each C3S grain. The pH rises to over 12 within few minutes, and which indicates, very alkaline solution. This hydrolysis, slows down quickly, but, continues throughout the induction period. Just keep in mind this curve right here. Then, stage 2, the induction period. When the calcium and hydroxide concentrations reach a critical value, the hydration products, calcium hydroxide and the calcium silicate hydrate, start to crystallize from the solution, and the reaction of C3S proceeds, rapidly, giving way to stage 3. The induction period, is apparently caused by the need to achieve a certain concentration of ions in the solution before crystal nuclei form from, which the hydration products can grow. This requirement is known as nucleation control. That's why this stage is known as nucleation controlled stage. The first one, chemically controlled, that means by the hydrolysis of the release of the ions. Okay, what happened here? Calcium hydroxide crystallizes from the solution, while the calcium silicate hydrate apparently develops at the surface of the C3S grain and forms a coating to cover the grain. Initial set occurs at the end of this stage, and in the first part of the third stage, about 2 to 4 hours. So in other words, and as has been suggested in some of the text and the literature, that in pure C3S, the induction period may be the length of time it takes for calcium silicate hydrate to begin nucleation, which may be linked to the amount of time required for calcium ions to become supersaturated in the solution. So that's one other explanation to the dormant period. Okay. Okay, so stage 3, well, this stage is also chemically controlled. The reaction of C3S again in this stage, it proceeds again, as mentioned above. This stage is chemically controlled, meaning hydrolysis of C3S starts again. The initial formation of hydration products begin, and after about 3 hours of hydration, the rate of calcium silicate hydrate formation increases with the amount of the calcium silicate hydrate formed. Also, what happened here, we have increased thickness of the hydrated layer, covering the C3S grain. Solidification of the paste, cold setting, occurs in this period for about 4 to 8 hours. Okay, then we have stage 4 and stage 5. These stages are diffusion controlled. So, and what happened as the hydration continues slowly, the thickness of the hydrate layer increases and forms a barrier through which water must flow to reach the unhydrated C3S, and through which also ions must diffuse to reach the growing crystals. This in stage 4. In stage 5, eventually mass transport through the calcium silicate hydrate layer determines the rate of reaction, and hydration becomes diffusion controls completely. The hydration, slowly continues, hardening the solid cement until the reaction is complete. One thing to remember, reactions that are diffusion controlled are quite slow and become slower as the thickness of the diffusion barrier increases. So hydration tends to approach 100% completion asymptomatically without seeing changes. Okay, so just to really shed more light and give more visual of what happened, this slide here shows a schematic representation of the process described above and the changes that occur to the C3S grain during hydration. As we can see here in each stage, what happened to this what first forms, the hydrolysis, the release of the ions, the formation of the initial calcium silicate hydrate, calcium hydroxide, and what happened, how the layer increases until it becomes diffusion control with time. So the takeaways from this, the mechanism of hydration is still really not 100% clear. However, the kinetics of the hydration is well understood. Several advances, through the use of X-ray tomography have been achieved. And as I said, some other theories have been offered as to the hydration mechanism. So just to be fair, to tell you, there are other probably theories that will vary slightly from what I described. Although the hydration, how I explained it here, is still taught in some textbooks, so it's still out there. So what you need to know, the 5 stages as shown in the table right here. You need to know the 5 stages. You need to be able to mark them on the heat of hydration curve here. You need to describe the kinetics and the mechanism of each stage and its relevance to the concrete properties. Okay, what happened, initial setting, hardening, the final set, and that kind of information. Okay, so just to remember one thing about the steady state stage, curing is very important in order to make sure the reactions in stage 4 and stage 5 take place. So that's one thing to remember. Okay. Okay, one thing I like to mention about the hydration of C3S and its how it's impacted by temperature. As you can see in these curves, the hydration of C3S is really sensitive to temperature, meaning there is an increase in the rate of hydration with the increase in temperature, but only when the reaction is chemically controlled. That means stage 3. Now, once hydration is completely diffusion controlled in stage 5, it is much less temperature sensitive, although the diffusion coefficient of the hydrate barrier varies with temperature. So it still has some relevance, but its impact more pronounced in stage 3. So, and also the overall effect, of the temperature on the hydration of C3S, as I said, is shown in this figure. As you can see, as you increase the temperature from 525 to 50, you see what the percent hydration, how it increases with time. Okay. Okay, so let's look at the hydration of the C2S, the dicalcium silicate. C2S hydrates in a similar manner, but much slower because it is a less reactive compound than C3S. The amount of heat liberated by the C2S is also lower than it is with C3S, and so its calorimetric curve is not easy to measure experimentally. So you need to remember that. However, I would like to elaborate more, in the comparison between the C3S and C2S hydration. if we look at the hydration equations of these two components I shown earlier, excuse me, and despite the fact that similar reaction products are formed, on hydration of both the tricalcium silicate and dicalcium silicate present in Portland cement, the following points should be noted. First, the stoichiometric calculations show that C3S hydration would produce 61% of the calcium silicate hydrate and 39% calcium hydroxide, whereas the C2S hydration would produce 82% calcium silicate hydrate and 18% calcium hydroxide. Interesting. So, as the high specific area and consequently the adhesive property of the hydrated cement paste are essentially due to the formation of the calcium silicate hydrate, it is to be expected that ultimate strength of a high C3S Portland cement would be lower than a high C2S cement. Okay, this is indeed, confirmed by the data from several research investigations. Second, if the durability of a hardened cement paste to acidic and sulfate waters is reduced due to the presence of calcium hydroxide, it may be expected that a cement containing high proportion of C2S will be more durable to acidic and sulfate environments compared to cement containing high proportions of C3S. So the conclusion is also, generally confirmed by laboratory and field experience. So from the standpoint of durability to chemical attacks, some cement standards attempt to limit the maximum permissible C3S in cement. And I have seen this, and I have also in my research shown C3S to be, I don't want to say harmful, it had some drawback when the C3S was higher, like 70%. Okay, so some cement standards limit the C3S content in cement. Others recommend the use of pozzolans, which we will discuss later, in order to remove the excess calcium hydroxide from the hydrated cement paste. Third point, that the stoichiometric equations for the C3S and C2S hydration do not tell anything about the reaction rates. The equations I've shown earlier. From the heat of hydration data, which I will show in the next slide, it is apparent that C3S would hydrate at a faster rate than C2S. Also, in the presence of gypsum, C3S and fine particles of cement begins to hydrate within an hour of the addition of water to cement, and thus it contributes to the final time of set and early strength of a hydrated cement paste. And again, gypsum has an impact. I will show those in later lectures. Also, okay, the relatively quicker rate of C3S hydration in finely ground Portland cement, has become an important factor in the production of high early strength Portland cements, as we mentioned, and we will discuss this later also. This is the table I just mentioned. If you look, these are the heat of hydration at given ages in calorie per gram for the various cement compounds. C3S, as you can see, compare it to C2S. It's much larger, of course. Of course, you have C3A and C4A. C3A, of course, the highest, because we mentioned that before, if you remember. It's very reactive and gives off much heat. But for the C3S and C2S, and you remember when we talked about the types of cement and the low heat of hydration cement, usually higher in C2S than C3S, etc. Okay, so let's move on Let's look at the hydration of C3A. As we mentioned, during the manufacture of cement lectures, aluminum and iron are useful as they work as fluxing agent, meaning reducing the heat demand within the kiln. However, the presence of C3A, as I have mentioned this several times, poses a problem since its quick hydration causes what is called a flash set. That's why gypsum is added to control and slow down this reaction. So in Portland cement, the hydration of C3A involves reaction mostly with sulfate ions, which are supplied by the dissolution of gypsum, typically gypsum added during the manufacturing of cement. So the reaction involved in the C3 and the hydration of C3A. The primary initial reaction of C3A, when ample amount of gypsum is present, is as follows. We have the C3A, tricalcium aluminate, plus gypsum, or a source of sulfate, typically gypsum, plus water. We will have this product, which is the calcium sulfoaluminate hydrate, the ettringite. This reaction is exothermic. Okay, this ettringite, which is the calcium sulfoaluminate hydrate, is the name given to a naturally occurring mineral of the same composition. That's where the name comes from. Ettringite is a stable hydration product only while there is an ample supply of sulfate available. The formation of ettringite, the benefit of it, slows down the hydration of C3A, basically by creating a diffusion barrier around unhydrated C3A particles. This is, analogous to the behavior of the calcium silicate hydrate during the hydration of silicates. But this barrier slows down the hydration of C3A and prevents the flash set. So let's look at the reactions involved in the hydration of C3A after that, primary reaction. So if all the sulfate is consumed before the C3A has completely hydrated, then ettringite becomes unstable and transforms to another calcium sulfoaluminate hydrate containing less sulfate through the following equations, which I have shown this equation before. The unhydrated C3A plus this ettringite formed earlier plus water will give us this sulfoaluminate hydrate. This second product is simply called as monosulfoaluminate hydrate. It has one S compared to 3 here. This is a trisulfoaluminate, this is the monosulfoaluminate. Okay. The monosulfoaluminate may sometimes form before ettringite if C3A reacts more rapidly with sulfate ions than they can be supplied by the gypsum to the mixing water. Okay, so that's another thing to remember. The diffusion barrier created by the formation of ettringite, then broken down during the conversion of ettringite into monosulfoaluminate, and C3A is allowed to react rapidly again. Okay. Okay, so when the monosulfoaluminate is brought into contact with a new source of sulfate ions, for example, external sulfate source, then ettringite can reform again as follows in this equation. And again, I showed this equation during the talk about the cement composition. So again, monosulfoaluminate with a sulfate source, water, we get ettringite. Okay, the potential for reforming ettringite really is the basis for sulfate attack of Portland cements when exposed to an external supply of sulfate. So remember that and be aware of that. So if the gypsum, let's assume, if the gypsum is not added in the cement, the hydration of C3A can lead to flash set, which I talked about it before, due to the rapid formation of calcium aluminate hydrates, calcium aluminate hydrate phases, according to this equation, for example. Tricalcium aluminate with water will give us, some form of calcium aluminate hydrate phases. Okay. These hydrates, the first two phases, are not stable and later may convert to another phase, the C3AH6, which is called hydrogarnet, according to this equation. So when a small amount of gypsum are present, there may still be unhydrated C3A present, when all the ettringite has been converted to monosulfoaluminate. In such cases, the monosulfoaluminate, reacts with the unhydrated C3A, forming, something like this called the monosulfoaluminate solid solution with this chemical composition right here, according to this equation. Okay, so there is plenty, of potential scenarios for various reactions that occur depending on the presence of the sulfate. So properly sulfated cement is a big deal, and you have to really be aware of what the sulfate or the ratio of the tricalcium aluminate to the sulfate present in the cement and its significance. So again, this slide here, I will show you the reactions involved in the hydration of C3A, the formation of the hydration products, and what I just said about the molar ratio between the sulfate and the tricalcium aluminate. What happened in each scenario? If the ratio about 3, we get ettringite. 3:1, we get ettringite and monosulfoaluminate. 1, we get monosulfoaluminate. Then we have real disaster here of potential exposure to sulfate ions again, and the formation of ettringite. If it's less than 1, we will get the monosulfoaluminate solid solution I spoke about earlier. If 0, we get the hydrogarnet phase, the calcium aluminate hydrate phases. Okay, so I'm really talking about this a lot because it is a big deal, and it has significant impact on the durability of concrete. Okay, so let's look at the calorimetric representation, for the hydration of C3A, which, basically, as you can see here in this curve, it looks, qualitatively much like the curve for C3S, shown earlier. So the first peak right here, the first heat peak is completed in 10 to 15 minutes. And then, the rate of heat evolution has been reduced to a very lower value, as you can see on the curve, due to the formation of the ettringite barrier. The heat of hydration remains at low value till the ettringite barrier is broken by the transformation of the monosulfoaluminate after all the gypsum has been used from, to form the ettringite. Okay. Then, the more gypsum there is in cement, the longer the ettringite will remain stable. So in most cements, ettringite remains in stable condition for a period of 12 to 36 hours. Also, the rate of heat evolution starts, increasing with the start of yttrium conversion to monosulfo-aluminate and reaches, to the second heat peak. And then again starts decreasing, approaching a steady state again. And I said, qualitatively, it resembles the curve of the C3S. Okay, and again, really just to be thorough, I want to elaborate more on the potential or the different scenarios of the hydration of C3A as compared to what happened in each case when we have various or different levels of sulfates in the cement. Okay, so as you can see here, for example, we have case 1. Okay, we have the availability of sulfate in solution. So what happened in this? We have low C3A or low reactivity of C3A, low availability of sulfate. So, okay, what happened? Less than 10 minutes, cement is workable, still workable 10 to 45 minutes. And about 1 to 2 hours less workable, 2 to 4 hours, we have, the normal set. Basically what happened here, the formation of yttrium. Case 2, we have high reactivity of the C3A and clinker, and we have high supply of sulfate. Again, it's still, the cement is workable for about 10 minutes, 10 to 45 minutes less workable because we will start, getting the formation of the yttrium. Case 3, high reactivity or high C3A, low sulfate supply. The cement is only workable for less than 10 minutes. Right away, quick set, more between 10 and 45 minutes, quick set will occur. And this is due to the formation of these calcium aluminate hydrate phases, or maybe some calcium aluminate sulfate hydrate phases, but in the pores, not enough to prevent a quick set. So if we have high reactivity or high C3A, none or very low supply of sulfate, we get flash set. And basically the formation of the calcium aluminate hydrate phases. On the other hand, if we have low C3A and high sulfate, we get a false set, which is basically the crystallization of gypsum needles in the pores. But this is false set, not flash set. So again, this is a good schematic representation I wanted to show to you guys so that you have really a visual and appreciate what happened in each scenario. Okay, so let's move on to the hydration of the tetracalcium aluminoferrite, C4AF. Okay, the tetracalcium aluminoferrite, forms the same sequence of hydration products as does C3A, with or without gypsum. As you can see to the first equation here, the potential with gypsum, the C4AF and water, we get a range of some product here with calcium aluminoferrite sulfate hydrate phase, or A plus aluminum ferrite hydrate phases. Or again, the remaining unhydrated C4AF will react with this product formed here with water, will give us another calcium aluminate ferrite sulfate hydrate and other aluminum ferrite hydrate phases. Okay, but the reactions are slower and involve less heat than C3A. Also, the C4AF never hydrates rapidly enough to cause flash set, and the gypsum retards the C4AF hydration even more drastically than it does in the case of C3A. Okay, with the increase in iron content in the C4AF, hydration of the C4AF becomes even slower. Okay, so practical experience, has shown that cements low in C3A and high in C4AF are resistant to sulfate attack. So this means the formation of yttringite from monosulfoaluminate does not occur in the case of C4AF. Some of the theories or some of the experiences have reported due to the presence of iron in it. Or alternatively, another explanation, the presence of the amorphous ferrite aluminate hydride phase up there may in some way prevent the reaction described earlier, the formation of the yttringite. Let me go back here to show you this reaction. It may prevent this reaction from occurring, and that is the explanation why it could be resistance to the sulfate attack. And again, this theory, I have not researched this really theory a lot, but it is out there, and anybody can do more research on it. Okay, so this is really the end of lecture 8. Next time we will start talking about the hydration of the Portland cement. Until then, thank you for watching, and we'll see you next time.